Okay, now we know how to create the major elements in a GaitSym document. I want to move on to showing you how to do something useful with it. What we're going to do in the next few short videos is create a new model and use it to calculate the moment arms of some muscles as you move a joint through its full range of motion, which is one of the things that GaitSym gets used for. So we're starting off with an empty GaitSym window. We create the new button by new document by clicking on the new button as usual, and in general nothing needs to be changed here until you become an advanced user. Then the easiest way is to create the model by importing the meshes as bodies, although you can create each body one by one. And here we go. I've created a special set of meshes for this. So I wanted to keep this fairly simple. So this is just two meshes around the hip joint, because we're going to do a couple of hip joint muscles. And obviously I could use one of the big complete models, but it would be much more confusing what was going on. So this is just a simple model. And if you just want a couple of muscles around a single joint, then you just need the bodies attached. The import option works really well for this because we're not doing a dynamic simulation, so we don't actually need to get the correct mass properties. And the ones that it automatically generates, from the bone outlines, whilst adequate for this, obviously are not numerically correct. So if you're doing a dynamic model, you'd have to do some extra steps. But for simply measuring moment arms, this is absolutely fine. As normal, being a little bit paranoid, let's save what we've got. We'll call it the moment arm model. Okay, so this is a completely sort of bare model, and we need a number of things to make it work. So we're looking at moment arms, and we're going to use the technique known as tendon travel. And we're going to do a sort of virtual tendon travel model. And in tendon travel, what you would normally do is dissect your chimpanzee or whatever animal you're interested in. And then what you do is you actually measure the length change of the muscles while you move the joint of interest through the angle that you're interested in. And you measure the angle of the joint and the length of the muscle. And by dividing one by the other, you get a value for the moment arm at that time. So it's basically the gradient of the plot of angle against length. So, and that's really easy information to get out of a model, and it's nice because you're doing an exact sort of virtual simulation of the standard experiment that's used to practically get moment arms. Now, the thing about that is that you do want to simplify your joints. So we're doing the hip joint, which is a ball and socket joint. But if you were doing this as tendon travel, you wouldn't just wiggle it around randomly. What you're interested in is the full range of extension and flexion, and you would do that separately in a separate experiment. And then you would look at abduction, adduction, and you would do that separately in a separate experiment. And then you would look at internal and external rotation, and again, you would do that separately. So effectively what you're doing is converting the ball and socket joint into 3 separate hinge joint experiments. And that's what we'll do here. So we'll first of all create a hinge joint that just does flexion extension, and then you just have to imagine that if you altered the angle of the hinge joint, you could do the other orientations. So we're mimicking what you would do in the actual experiment. Okay, so the first thing we have to do then is create the necessary hinge joint. So let's zoom into our model and we'll start working on that. So to create joints, you need markers. One marker attached to this sort of upstream body, which in this case would be the pelvis, and one marker attached to the downstream body, which in this case would be the left femur. So we need to create those. Now, it's a little bit challenging because what we've got is a ball and socket joint, and the center of this joint is in the middle of the head of the femur, which obviously, we can't easily directly put a marker on. But in fact, we can use the construction tools built into GaitSym to make this fairly straightforward activity. So this is the head of the femur. If we turn off the visibility of the trunk, you can see it a bit more clearly. And we know that this is a ball, this is a sphere effectively. And so the center is going to be halfway between a point at the center of this circle viewed from the front and the center of this circle viewed from the back. So we can create a marker here, and it's simply a construction marker, so we can leave everything on its defaults. And then we can flip the view around to the back, and we can put another marker where we think the center of the head of the femur is here. And again, we can leave that as defaults because it's just a construction marker. Now we can get on with creating the head of femur marker. Now it's going to be halfway between the two markers that we've just created. So if we go to create marker, we can use, well, we can give it a name this time, we're going to keep it. It's the left hip joint. And we're going to have to create two markers in this position, one for each body. This one we're going to attach to the thigh. Hip joint marker 1, and we're going to make it halfway between the two construction markers we just created. So this is what interpolate construction does. This is the fraction is a half, and this will create a marker exactly halfway between those two markers, and it puts the values in there, and we can create it, and there you'll see we've got this third marker now exactly in the middle. And I'll just save it there because you never know. Right, so that's one of the markers that we need. Now the thing about the way these work, so let's just get rid of those. Well, not get rid of, let's turn them in. If we look at where we are now, what we've got is we've got the X in red, the Y in green, and the Z in blue. So those are the axes of that marker, and they're the default ones lined up. The X in our particular model is the animal going forward. And of course, if what we wanted to do was look at abduction, adduction, that would be fine because the hinge joint aligns along the X-axis. But I want to look at extension flexion because it's by far the most interesting, and it's going to be easier to demonstrate. So the marker as it is at the moment won't do that. It obviously needs to be rotated. So what we need to do at this point is we need to edit the marker, and to make it point the right direction, we need to rotate it along the vertical axis. So the vertical Z axis we can rotate along, and we can do that by putting in 90 here, and that will rotate brilliantly, and that will now produce the axis where we want. And the final thing is, obviously, that's the marker that's attached to the thigh, but we also need a marker in exactly the same place, in exactly the same orientation, attached to the pelvis, to the trunk. So we need to create that marker. And we do that by selecting the marker we want to copy, and then we can just copy marker 1 down here. It doesn't do any interpolation unless we hit the calculate button, and so this is an exact copy. And this is left hip joint marker 2. And you can show that they're both there because we have to hide both of them to make it work. And then the final step at this point is to create the hip joint, which is create joint. It's a hinge joint running between hip marker 1 and hip marker 2. And now we want to have some stops. So we know that the maximum extension is maybe minus 20 degrees, and the maximum flexion is quite high, probably as much as sort of 135 degrees, if not higher. So we can put the range in there. Now the signs of these are important. There is a wrapping direction, but I always forget which it is. So the easiest way is to put some values in, and you've got a 50-50 chance of being right. And then if you're wrong, you can always just go back and edit them and reverse them. And I just find that's a lot simpler than sort of thinking in my head about right hand rules and wrapping and so forth, and it's very, very easy to get it wrong, and it's much, much more sensible just to have a guess which way around it might be, and if you're wrong, it's obvious from the graphic, and then you can go and fix it. And once you put a few joints in, actually you don't get it wrong anymore, but the first one, it's always a bit of a guess. And there's the joint created. We can turn the back on, and we can see we've got a nice hinge joint that will restrict the movement here to flexion and extension. So I'll stop it for there, and then next one I'll show you how to attach muscles to this, and then how to move the joint through its range of motion.